Good afternoon. Today we will start the topic Coulomb's law, right? So Coulomb's law applicable to the point charges at rest. Consider 2 point charges Q1, Q2 in rest. These are point size, right? Separated by a distance small r in vacuum. The Coulomb's law states that each charge in rest attract or repel exerts a force on the other, which is given as, firstly, it is proportional to the product of their magnitude. Secondly, it is proportional to the inverse of the square of the distance between them. When we combine this is f equal to small k, proportionality constant called electrostatic constant, right? And formula becomes small k q1 q2 by r square, where small k is proportionality constant 1 in CGS and 9 into 10 power 9 in SI unit system. Units are Newton meter square per Coulomb square, right? Newton meter square per Coulomb square, right? One more way to write small k, it's 1 upon 4 pi epsilon 0, right? Small k equal to 1 upon 4 pi epsilon 0. 4 pi is unit solid angle and epsilon 0 is called permittivity of the free space. Permittivity of the free space, mathematically value is 8.85 10 power minus 12 Coulomb square upon Newton meter square, right? So the formula first, that is Coulomb's law, can be written as 1 upon 4 pi epsilon 0, right, into q1 q2 by r square. q1 q2 by r square, right? So if two charges are placed in a medium, then the formula becomes 1 upon 4 pi epsilon. Epsilon 0 is now replaced with another parameter. This is permittivity of a medium, right? It's q1 q2 by r square. So divide second by third. So this is force in vacuum. I call it F0, right? So this is force in a medium. So q1 q2 and r square cancel out. 1 upon 4 pi cancel out, and this become epsilon upon epsilon 0, right? This ratio is known as dielectric constant or relative permittivity. Epsilon by epsilon 0 can be written as capital K, usually known as dielectric constant. Epsilon r known as relative permittivity. Capital K is usually 1 for vacuum. It is 1.0008 for air, and this is infinite for metals, right? This varies from 1 to infinite. This cannot be less than 1. That's why in general force between two charges would be maximum in air. When two charges are placed in vacuum, you can go for 1 mark question. The two charges placed in vacuum having a force between them F. What would happen when they are placed in any medium, right? So this force would be reducing. In any of the medium other than vacuum, the force always reduces. Am I clear? This is one part. We have certain characters of Coulomb force. We can list them, right? So look at the part. First, Coulomb force is the weak force in nature, right? Second part, it's a long range force. Third part, it always acts along the line joining. You can call it central force. Next part, the force between two charges depends upon medium. Vacuum में अलग थी, medium आने पे अलग गया. So it depends upon the intervening medium. Right? Am I clear? Superposition principle applicable. Superposition principle applicable for the Coulomb's law. If there are so many charges, if a charge Q0 surrounded by few charges Q1, Q2, Q3, then the net force would be equal to vector sum of the individual forces F2 plus F3 and so on. Done? Now we'll go for a one numerical practice based on this topic. I hope this topic is clear. Let me go for a very simple numerical based on this Coulomb's law. Consider two charges, right? So consider two charges. It's numerical number 1. Two charges, one is 40 microcoulomb, second is 10 microcoulomb. It's okay, separated by a distance 10 centimeter in vacuum. Now, where should we place third charge Q0 so that it does not experiences any force or it remains in equilibrium? You have been provided two charges. One is 40 microcoulomb. You can call it Q1. You can pause the video and try this, and after that you can go for the solution. Right? Q1 is 40 microcoulomb. Q2 is 10 microcoulomb. Distance between them is 10 centimeter. It's okay. Where should we place a third charge Q0 so that it does not experience any force? For this, let me start. You can first try. Then you can go for the solution. You can pause it. Wait for 2 minutes, try this, and then go for this question. Right? So the solution is the distance x. The other distance is 10 minus x. If this is Q0, both would be either attracting or repelling. If it is negative charge, both would be attracting. If it is positive charge, both would be repelling it. Right? So in that case, in equilibrium, F1 must be equal to F2. You can write this in vector form also, but let me use the magnitude. F1 must be equal to F2. So F1 is small k into 40, 10 power minus 6, Q0 upon x square. What about the other? It's k 10 into 10 power minus 6 into Q0 and 10 minus x square. Right? K cancel out in both sides. Q0 cancel out. 10 power minus 6 cancel out. Next 1 0 cancel out. Cross multiply. 4 into 10 minus x square is equal to x square. Right? Taking square root on both sides. Twice into 10 minus x is equal to x. Right? It's 20 minus 2x is equal to x. It's 20 is equal to 3x, or x is equal to 20 by 3 centimeter from, you should mention it, we have chosen x from the 40 centimeter. So we should write at the end from 40 microcoulomb charge. One may use x here from the 10 microcoulomb. So the answer would be 10 minus 20 by 3. So you should mention at the end, it's 10, whatever the answer, from 10 microcoulomb. I hope it is clear. This is the first category of question. Right? Let me go to the next category. Right? So, go to the numerical number 2. Consider 3 charges. Here, charge is Q. Here, charge is Q, and here another charge capital Q. It's a triangle, equilateral triangle, each side is L. 3 charges are placed on the vertices of a triangle. Calculate net force on the capital Q. Right? So the question is, calculate net force on the capital Q. Again the same way, you can pause the video, try this, and then again replay the video. Right? So the solution. So for this, let me first calculate first force due to this Q. May I mark it A, B, C. Force on C due to A. So this would be repelling. May I call it FA? This charge also would be the same nature, that's why it is repelling. So FB. Let me apply Coulomb force. FA is K capital Q small q upon L square. What about FB? This FB is K Q by L square. Both are equal by the choice. You may take different sign, different amount, right? The complexity can be increased or decreased. So that's your homework you can try. Try here with the 2q charge, minus 2q, or sign change in both. Both are attractive, both are negative. It's okay. So here, come back. So FA, FB, both are equal. Now look at the part. If it is an equilateral triangle, this angle is 60. So this is again by the property of vertically opposite. Now the two forces equal in amount. FA equal to FB. Let me call it F, as both are equal, right? So both two forces act at 60 degrees. Then the net force would be under the root F square, triangular law of vector addition, plus F square plus twice into F into cos 60. I hope it is clear. We have studied this formula in class 11th. Applying this. So this is F net. So this is twice F square plus twice F square. Cos 60 is half. Cancel out. So F net would be it's a 3F square. So ultimately the answer is F net is root 3F. Or you can put the value F net is root 3 times of K Q by L square. Now you can try yourself this question by changing the data. Let Q is 10 microcoulomb, this is 20 microcoulomb, this one distance is 10 centimeter or 5 centimeter. Right? That's all. Thank you everyone.